Hello, hello, hello. In Introduction to Photonics course project, I am assigned the course project as the photonic crystal design and fabrication. And so in this course, I have simulated the photonic crystals and with the variation of refractive index of different materials and different and we have observed for different wavelengths. So what is photonic crystal? A photonic crystal is a periodic structure in which the refractive index varies spatially on the scale of the wavelength of light. This periodicity creates a photonic band gap, that is a range of wavelengths where light propagation is forbidden. So that is similar to how an electron band gap works in semiconductor. Photonic crystals are used in uh, Photonic crystals are used to manipulate the propagation of light by controlling its reflection, transmission, and confinement. So, as we can see in this diagram, it is a periodic structure of several holes. That holes are made up of gallium arsenide in this case, and that gallium arsenides are surrounded by air medium, and that forms the photonic crystals. But in this case, a defect in photonic crystal is an intentional disruption in the periodic structure, such as missing rod hole or variation of lattice spacing. These defects allow light of specific wavelength to propagate or be confined in the defect region. So in this case, we see there is a defect is introduced in the photonic crystal. So we can in this so if the wavelength if the if the wavelength is supported by the photonic crystal, it will generally penetrate through this defect region. So now we will check we will first we will give the wavelength, and then we will check whether the light wavelength will pass through or not. So in order to do so, we have to go to the wavelength domain, and uh, I have assigned 1 micrometer wavelength, and then just compute it, and after a few minutes we will see the result. Yeah, so as we can see, the wave is completely passing through the device, passing through the crystal. That means there is no leakage inside the photonic crystal. The wave is completely following uh, the confined region of the defect, basically. So that means the 1 micrometer of wavelength is supported by this wave photonic crystal. But and also we can this is the surface plot of electric field. Now if I want to see the linear graph of the electric field with respect to the arc length, we see that there is a oscillatory nature. That means the wave is passing, there is no decaying nature, so that means the wave is propagating through the devices. Now if I change the wavelength to 1 to 1 point, let's say 5 micrometer, and compute it. So the computation is done. So for 1.5 micrometer, we can see that this wavelength cannot propagate through this photonic crystal. So it is because it is completely decaying out, and it is leaking through the entire photonic crystals, and it cannot propagate through the devices. So we can check this from the linear graph as well. In the linear graph, we see the electric field normal vector is decaying out with respect to the arc length. That means it cannot propagate through the device. So by this observation, we can say that the photonic crystals has some frequency selectivity, because it is selecting one particular wavelength and not others. um, so now we can vary the refractive index for other materials as well. So how to do so? we have to go to the materials and then browse materials, and we search for different materials. Like for example, we are searching for silicon nitride and search it, and we get different silicon nitride, any one we can select. And I have already computed those results. So let us check. So this is basically the result of silicon nitride, and it is computed for 0.77 micrometer. And as we can see, this wavelength is barely supports this wavelength is supported by the photonic crystals, and it is clearly passing through the device. And also the linear graph shows there is a oscillatory nature, so that means the wavelength is supported for for this device. If now in the next case I have changed it to 1 micrometer, from 0.77 to 1 micrometer, but now we see that the wavelength is not supported here, because there is a leakage, completely leakage, and the linear graph shows that it is completely decaying out from, with the arc length. That means here also, uh, if I change the refractive index, if the change if I change the material to silicon nitride, the 0.77 micrometer of wavelength is supported for this device. And also if I change to another material, let's say gallium nitride, the in the case of gallium nitride, we see 0.8 micrometer wavelength is supported. So the wavelength, the wave is completely passing through the uh, confined region of the photonic crystals, and the linear graph also shows that there is a oscillatory nature. So uh, that means it is 0.8 micrometer is suitable for this. And another wavelength, let's say 1.5 micrometer, it is not supported because there is a leaking, uh, it is leaking to the photonic crystal. So that means why there is a frequency selectivity for the photonic crystal, because when the light falls in the band gap, optical band gap region, so it will not allow it to pass through, because the wave will be completely reflected back to the from the devices. But if the light falls in the pass band region, it will only allow the light to pass through. So that means here in this case, in the gallium nitride case, 0.8 micrometer falls in the optical passband region. So that's why the light is passing through the device. Otherwise, if I use 1.5 micrometer, it will not pass, because it lies in the optical band gap region. So by this, the photonic crystals has the property of guiding the wavelength, guiding the wavelength. So from this observation, we can see that the photonic crystal has the guiding nature of wavelength. So basically, by using this property, we can sharp 90-degree bend the optical wave that cannot be possible in optical fiber. Because if I use 90-degree sharp bend, there will be some finite number of leakage, finite amount of leakage. But in this case, it cannot the leakage is very less. I mean, there is a negligible leakage, because the wave is completely passing through without any attenuation or any leakage property. So, and also this property can be used in optical fiber. If I just use this defect use this confined region in a core region of the optical fiber, so it can pass a very long distance without any attenuations. So at the end, the observation shows that theoretical results is completely, I mean, the simulation results are well satisfying the theoretical results of the photonic crystals. So yeah, thank you.